Okay, as a last little bit, let's briefly apply this to proving some things about programs and algorithms. The bigger picture here is there's some applications where you really want more confidence in a piece of code than the programmer said, yeah, it looks good. And that's where formal verification can be applied. So you formulate in these kind of statements for all x exists y and all these things, you formulate what the program should do. And then you try to formally prove that. We won't do that to the full detail because it gets very tedious and is quite a topic of its own. But we'll touch on two things that are usually necessary for that. Correct usually means two things. First of all, the code actually finishes its job eventually. And if it does, then it computes the correct result. So I'm thinking of systems that have a clear input computation, output behavior. They compute some function. There's other theories about other systems that continuously run and fulfill some purpose. This is not what we're talking about. In a way, the formal verification we need here is there's something that you assume at the beginning of the program, then the program runs and does its job, and then at the end something should be true. So that's precondition and postcondition. That's what we usually have in mind here. So there's some assumptions that the algorithm makes. For example, the parameters of a function, the input value has to be a positive number. Then the code executes something, and that leads to a postcondition that hopefully has some value to you. We'll see examples. For the first bit, I just want to briefly touch on how you can do this. We'll do some example in the tutorials then. Suppose you have some function, a procedure in my pseudocode lingo that is recursive, so it calls itself. It could be our Towers of Hanoi solution, for example. And you want to prove that it eventually stops, right? A recursive function could keep calling itself. The formal way to prove that is to define a potential, some quantity that keeps going down but cannot go down indefinitely. So the important bit here is that our potential is a natural number. And natural numbers famously stop at 0. There's no way to go further down. So if you can somehow prove, I should have mentioned the parameters. So the potential exactly depends on the parameters to the function. Say in our Tower of Hanoi example, you call it with the number of disks that you want to move and probably also where they are. So what's the current pole that they lie on and what's the target pole. That's the parameters of the function. And then the potential can depend on those parameters. What you try to prove then is whenever the function calls itself recursively, like Tower of Hanoi, move this there, then do the red move and then move it back to the middle. In all these cases, the potential drops by at least 1. It strictly goes down, and because it's a natural number, that means it drops by at least 1. Okay? So example from Towers of Hanoi, the potential could just be the number of disks. Whenever we call ourselves on a stack of disks that's 1 shorter. That proves that we have to finish with this recursive call eventually because we always go 1 step down. So at some point we reach no disks, and then the procedure can just return. Okay? The idea is more versatile. The potential can be more complicated and depend on the parameters in interesting ways. You'll see an example in the tutorials. Yeah, I think that's basically all on this potential. It's just a convenient way to make the notion rigorous. That's when you recursively call something, you should somehow make something smaller. You can apply the same trick to a loop instead of a recursive call. If you have a while loop, might never finish. But if you can show that some potential function that's defined on the variables of the code there goes down in each iteration of the while loop, then it must terminate. Okay. The second bit, this is about correctness in the sense of computing the right result if it terminates. In this case, we'll talk about these pre and post conditions. And I picked out the most interesting case of that. So often pre and post conditions, they say something about the values of variables. And for simpler statements, like if the statement is x is assigned to x plus 1, increment x by 1, then if the precondition said something about x, you know what the post condition will be. It says the same thing, just where the value of x is updated. So if the precondition was saying x is at least 5, then the post condition would be x is at least 6, right? If we increment x by 1. These kind of statements, there it is easy to go from what is true before to what can we guarantee after. It gets very tricky with loops. And that's the example I want to pick out here. For a general loop, a while loop, you need to work a little harder. So the setup here is we have some position before a loop, and we know there's some assumptions we make what is true before the loop. Then we have a while loop with some condition, it does something, and then we want to guarantee some statement after the loop. I'll have a more concrete example on the next slide. I wonder if we have to push the example to next week, though. Let me walk you through the sequence of steps you have to do in this case. The trick here is to find some condition called the loop invariant, for which you can prove a few things. You can prove that it is already true before the start of the loop. It is true again after the body of the loop, but here you can assume that you are in the loop. So you can additionally assume the condition of the loop to be true. And you also want to be able to prove that the same invariant is true after the loop. That sounds a bit abstract, I guess, right? But that's a way. It's a formal strategy. Whatever I is, if you can prove these things, then you can hopefully get some desired post condition. Let me at least show you the concrete example. And I think we'll do the proof applying the principle here. We'll do next time. This is a little innocent function that takes an array and finds the largest value in the array. And how would you do this? Well, not too hard. You start with you keep the current value, you go through the list, and you always store in the variable what's the current largest. Okay. And so current maximum, I guess the name suggests it, holds that current maximum. And so initially that's the first element. And then we do a loop until we haven't reached the end of the array. We check if the current element in the array is bigger than what we previously had as the maximum. If so, then that should be the maximum, at least for now. And otherwise, we don't change it. And so you run through this, and you eventually return current max. You probably agree that this code is super easy, and it's quite obvious that it's correct. However, we've already had obvious code, and it wasn't correct, so maybe we should be careful. In this case, it is correct. There's no hidden nastiness. But what I want to do is walk you through the precise steps if you need it to show very rigorously that this computes the right thing. And often along the way, we notice that there are some corner cases and side conditions that are easy to miss, like calling this function with an empty array is not a good idea, right, if we access the 0th element. Question?
seems to me that this technique for proving correctness of iterative procedures is generative. Like, if I want to design an algorithm to do something, I can use this invariant technique. I can like construct my invariant. I can like pick something, ensure that property is true before the iterative sub procedure, and then construct the iterative sub procedure such that the property remains true, and ensure that property is true after. So like I can use the proof technique to generate a correct algorithm to do something. Like using the invariant.
Okay, so this, yeah, I mean, the question is maybe a bit two questions. So one is, can you automate the proof? Can you automatically find the proof? And can you use that to find the algorithm, right? Yeah, so it's the tricky bit in this case, the part that is not automatic or where there is human insight needed fundamentally is finding the loop invariant. There's nothing in the template. If you check here, this template lists a few things. I want this and this and this and this. It doesn't tell you how to find the loop invariant. And the reason is no one knows a strategy to do that automatically. It seems not so easy possible, at least not in general. It seems not possible to tell a computer these are the steps, then you have your loop invariant. In some limited case, it's definitely doable, but not in general. And also what happened to me when I wrote up this proof, I had the first part of the loop invariant and was missing the second. And then you notice you're somehow stuck and you need to add something else to the invariant. Yeah, I think we should come to a close, and I don't think I can do this in 1 or 2 minutes. So let's postpone the detailed example for next week.